One hot encoding works very well for most problems, until you get into situations where you have tens of thousands or even millions of classes. In that case, your vector becomes really, really large, and it has mostly zeros everywhere, and that becomes very inefficient. You'll see later how we can deal with these problems using embeddings. What's nice about this approach is that we can now measure how well we're doing by simply comparing two vectors. One that comes out of your classifiers and contains the probabilities of your classes, and the one hot encoded vector that corresponds to your labels. Let's see how we can do this in practice. The natural way to measure the distance between those two probability vectors is called the cross-entropy. I'll denote it by D here for distance. In math, it looks like this. Be careful, the cross-entropy is not symmetric, and you have a nasty log in there. So you have to make sure that your labels and your distributions are in the right place. Your labels, because they're one hot encoded, will have a lot of zeros in them, and you don't want to take the log of zeros. For your distribution, the softmax will always guarantee that you have a little bit of probability going everywhere, so you never really take a log of 0. So let's recap, because we have a lot of pieces already. So we have an input. It's going to be turned into logits using a linear model, which is basically a matrix multiply and a bias. We're then going to feed the logits, which are scores, into a softmax to turn them into probabilities. And then we're going to compare those probabilities to the one hot encoded labels using the cross-entropy function. This entire setting is often called multinomial logistic classification.